Section: Introduction. In this section, we discuss next token prediction, NTP, which is the main goal for training sequence models. This process uses a technique called teacher forcing, where we replace the model's predicted output at each step with the actual output from the dataset. One advantage of teacher forcing is that it speeds up training by providing the correct previous output, preventing errors from building up and making gradient updates more stable. Additionally, it allows for parallel processing during training, as the model can handle all time steps at once instead of waiting for its own predictions. However, we note that models trained with teacher forcing often struggle to learn long-range dependencies, focusing instead on local patterns and surface-level correlations. To address these issues, several recent methods have been introduced. One common approach is multi-token prediction, where the model learns to predict several tokens simultaneously. Other methods modify the training objective to predict both the next token for a prefix and the previous token for a suffix, which can complicate the learning process. In our work, we explore a data-centric approach to overcome these limitations. Instead of changing the model architecture, we modify the training data by introducing special tokens that provide future information. Specifically, we enhance the training set by adding look-ahead tokens that help the model learn long-term dependencies and plan ahead. The placement of these tokens can be random or based on specific task knowledge. We believe this method not only simplifies the learning of long-term dependencies but also allows users to control the generation process more precisely. Our contribution is a straightforward data rearrangement technique called TRELAWNEY, which improves performance in tasks that are challenging for models trained with next token prediction. We present results on tasks involving planning, algorithmic reasoning, and conditional story generation. Next, we consider a sequence of tokens, where each token belongs to a fixed vocabulary. We assume that this sequence follows a certain distribution, and an autoregressive model breaks down the joint probability of the sequence into a product of probabilities for each token based on the preceding tokens. During training, we aim to maximize the likelihood of each token given the correct context using teacher forcing. If our training data consists of multiple sequences, we estimate the model parameters by maximizing the sum of the log probabilities of each token. At inference, the model predicts the next token by either sampling or selecting the most likely one based on an optional context. In a greedy approach, the next token is chosen as the one with the highest probability given the previously generated tokens. We also highlight some pitfalls of teacher forcing. One issue is the clever Hans cheat, where the model can cheat by copying easy tokens instead of learning the underlying plan. Another problem is the indecipherable token problem, where early decisions receive insufficient feedback, making them hard to predict. Finally, exposure bias occurs during inference, as the model may make mistakes due to the mismatch between training and inference conditions, leading to a series of errors. Section Summary. In this section, we discuss the limitations of next token prediction, NTP, using teacher forcing, which accelerates training but often hinders the model's ability to learn long-range dependencies. We introduce our data-centric approach, TRELAWNEY, which enhances training by interleaving special look-ahead tokens in the data, aiming to improve task performance and enable better long-term planning without altering the model architecture. Section: TRELAWNEY. In this section, we introduce a data augmentation method for standard decoder-only transformers, which typically learn to break down a sequence. Our approach modifies a given sequence, denoted as Y, by selecting a point D and inserting a sequence of K tokens, represented as Z, surrounded by special tokens less than T greater than and less than T greater than. We have flexibility in choosing D, K, and the content of Z, and we outline several strategies for this augmentation. One strategy is copying, where we can take a part of the sequence from after Y_D and place it between the special tokens. For a position S that falls within a specific range, Z becomes the subsequence from Y starting at S and extending for K tokens. The choice of Z can greatly influence the model's behavior. For instance, certain data types have decision points with multiple possible outcomes, making them ideal for selecting D. We can also choose Z to represent future tokens that indicate which outcome is being generated. These definitions are intentionally broad due to the vast design space. Alternatively, we can randomly select D, S, and K, which can be beneficial for general language modeling. However, we recognize that varying D and S across different data points can create challenges, especially if two sequences have significantly different values for S minus D. This discrepancy can complicate the modeling task due to conflicting information. For example, if two sequences share the same prefix but have future tokens located far apart, we introduce additional positional information into the future tokens, denoted as zeta, K, Z. The exact design of this positional information can depend on the specific problem, and it doesn't need to be perfectly accurate as long as it reduces potential conflicts. We can also copy text from the future, but it doesn't have to be identical, as long as it conveys relevant information, such as a paraphrase. We express zeta in natural language to allow the model to integrate it with its pre-training knowledge and enable users to set different goals. We can also use special tokens for this purpose and explore various agentic behaviors through zeta, although our investigation in this area is still preliminary. Regarding dataset construction, our aim is to enhance capabilities through the augmentation schema without compromising the model's traditional language modeling skills. We achieve this by training on both original and augmented text simultaneously. Given an original dataset D and an augmentation schema, we create distributions for both the original and augmented datasets. By controlling the probability P, which determines the proportion of original data in the training distribution, we form a mixture of the two datasets. During training, we optimize the model parameters using a standard cross-entropy loss with teacher forcing on the combined dataset D. However, we must be cautious, as arbitrary choices for decision points and future tokens can lead to many sequences where the next token is less than t greater than at random locations, which could hinder the learning process. To address this, we modify the cross-entropy loss by masking the special start token less than t greater than, ensuring that no loss is computed for its prediction. We still include the loss for predicting less than t greater than because it is useful for determining when the future tokens end, which we will discuss further. Section Summary. In this section, we introduce a data augmentation scheme for decoder-only transformers that involves inserting flexible sequences of tokens into existing sequences, which can enhance model performance by providing additional context. We also discuss the construction of a training dataset that combines original and augmented data while ensuring effective learning through a modified loss function that accounts for special tokens. Section Inference. In this section, we discuss inference and our approach to standard autoregressive generation. Our model generates sequences in an autoregressive manner without any external intervention, using standard decoding algorithms. We introduce a method called less than t greater than generation, which allows the model to consider future context at key decision points, enhancing its planning capabilities. At each decision point, we insert a special token less than t greater than. This enables the model to either generate a sequence on its own, creating plausible future plans, or to use a user-defined sequence, which improves controllability. During training, we focus on the loss related to the less than t greater than token, allowing the model to generate future goals for conditional generation. Unlike existing methods that require specific decoding techniques, our approach can utilize any standard decoding algorithm. We hypothesize that focusing on challenging tokens or strategic goals can enhance the quality of generation. To test this, we conduct experiments across 3 tasks, both synthetic and natural language. The synthetic tasks provide a controlled setting to study specific challenges that are hard to separate in natural language. We start with 2 synthetic benchmarks: the star graph, which illustrates the limitations of next token prediction in simple tasks, and an algorithmic reasoning benchmark, which helps us assess whether adding future goals improves performance in reasoning tasks. We also explore story generation to evaluate controllable generation and planning. Our experiments aim to answer several questions. Does our method, TRELAWNEY, enable the generation of long-term goals? Does Trelawney training enhance planning during autoregressive inference? Do the goals generated by the model improve planning? Does providing goal sequences improve controllability? The star graph presents a straightforward pathfinding challenge where we need to find a route from a starting node to a goal node. Despite its simplicity, traditional next token prediction struggles with this task, particularly at the first decision point, which is difficult to predict due to multiple outgoing edges. We introduce a future subgoal, which is a segment of the path, to encourage the model to create meaningful intermediate plans instead of just copying the full path. Each example in our dataset consists of a prefix and a completion pair, where the prefix includes the graph's adjacency list and the start and goal nodes, while the completion is the actual path taken. We vary the future subgoal across experiments to guide planning without directly including the first decision point or the goal, allowing the model to learn long-term dependencies. Our training data is generated programmatically, and we use pre-trained models, treating each node as a single token. We train on 200,000 examples using standard teacher forcing with two augmentation strategies: Trelawney fixed, where the subgoal is consistent across examples, and Trelawney random, where the subgoal varies randomly. We evaluate our models on 5,000 held-out examples, comparing the generated paths to the ground truth. For the baseline, we use standard autoregressive generation, while for Trelawney, we assess both standard generation and less than t greater than generation. This allows us to see if Trelawney improves regular generation and if the model can generate plausible future goals for better planning. Our results show that training with Trelawney enhances autoregressive generation for shorter graphs, indicating that the model learns to plan better. For longer graphs, the Trelawney random variant successfully completes tasks by generating its own subgoal sequences, suggesting that model-generated goals can improve planning. We find that the random variant performs better on longer paths, likely due to its flexibility in selecting future goals. Both Trelawney variants succeed when user-provided goal sequences are used, demonstrating that explicit goal hints improve controllability. Further analysis indicates that larger models show improved planning capabilities for future tokens. Section Summary. In this section, we describe our approach to autoregressive sequence generation using a special token less than t greater than to enable the model to consider future context and improve planning. Our experiments, conducted on synthetic and natural language tasks, demonstrate that incorporating future goals enhances generation quality and controllability, with results indicating that our method outperforms traditional next token prediction, especially in longer planning scenarios. Section: Algorithmic Reasoning. In this section, we discuss algorithmic reasoning, specifically focusing on the CLRS text benchmark. The input consists of the algorithm's name, a detailed reasoning trace, and the final answer. We select a representative example from backtracking algorithms, particularly strongly connected components, which is a sequential prediction task where each step involves more than one token. We present the execution of Tarjan's algorithm, which efficiently computes strongly connected components using depth-first search, tracking low link values and utilizing a stack to identify cycles. For our dataset, each example in the strongly connected components subset includes a prefix representing the adjacency matrix of the initial graph and a completion that consists of the algorithm's execution traces followed by the final answer. Our augmentation schema helps capture intermediate reasoning steps by breaking the trace into meaningful units, which aids the model's planning throughout the execution. We simplify the decision point by fixing it at the second state in each trace. Unlike the star graph task, where failure points are clear, algorithmic reasoning tasks can have multiple points of potential error. We select a complete step from the trace as our decision point. In our training process, we use a subset of the original dataset, training a single model on various problem sizes. We report accuracies only for the sizes present in the training data, with 60,000 examples for strongly connected components. We explore two variants of our method: Trelawney rule-based, where the first change in the trace is chosen, and Trelawney random, where a random state is selected. For evaluation, we assess 500 examples per graph length, similar to the star graph setting, and report the accuracies of the final answers. Our results indicate that TRELAWNEY random consistently improves next token prediction, even in standard autoregressive generation, while TRELAWNEY rule-based performs worse despite its strategic selection. We also touch on related work in next token prediction, highlighting two types of failures, those from teacher-forced training and those that occur during inference. Previous research has mainly focused on inference time errors, while we note that tokens contribute unequally to performance. We mention architectural changes aimed at improving planning, such as predicting multiple n-grams and using additional encoders for simultaneous state representation. Our work relates to controllable generation, where models follow high-level goals without needing curated datasets or classifiers, achieving fine-grained control. We also discuss non-causal sequence modeling, which allows the model to utilize both past and future context, enhancing long-term planning in various tasks, including video prediction and world modeling. Section Summary. In this section, we introduce CLRS text as a benchmark for algorithmic reasoning, focusing on strongly connected components and the execution of Tarjan's algorithm. We detail our augmentation schema to enhance model training by capturing intermediate reasoning steps and evaluate our approach using two variants, TRELAWNEY rule-based and TRELAWNEY random, highlighting the latter's superior performance in next token prediction. Section Discussion. In this section, we introduce a method aimed at enhancing controllable generation. Our experiments with small-scale fine-tuning have shown effectiveness, but they are currently limited to synthetic or controlled environments. The initial results indicate that our approach could be adapted for broader applications, which we plan to explore in future work. Additionally, our method allows for the use of reinforcement learning to guide generation based on the information provided by special tokens. A key challenge we face is figuring out when the model should utilize these capabilities, and we believe that uncertainty metrics could provide a valuable solution.